everyone. Today I'll be tackling the first objective on modular arithmetic. So modular arithmetic deals with remainders when dividing integers. For instance, in modular arithmetic, 7 modulo 3 is 1 because 7 is divided by 3. The remainder is 1. Does that make sense so far?
Yeah, that makes sense. Modular arithmetic is like working with clocks, right? Where numbers wrap around after reaching a certain point.
Exactly, Carl. It's like the hours on a clock. So if it's 10 o'clock and we add 5 hours, what time is it?
It would be 3 o'clock because we're working with modular arithmetic and the hours wrap around after 12.
Perfect. That's the essence of modular arithmetic. Problem together. How about we tackle a simple equation like 12 modulo 5?
So our second objective is functions. Alright, let's dive into function. A function basically relates each input to exactly one output. It's like a machine that takes in an output and gives you an output. For instance, if we have a function f at x is equal to x and we input 3, what's the output?
The output would be 6 because 2 times 3 equals 6.
Precisely, Justin. Now, there are different types of functions, like one-to-one and onto functions. A one-to-one function means each input a unique output, and an onto function means every element in the output set is mapped to by at least one element in the input set.
So, if we have a function f of x equals x squared, is it a one-to-one function?
No, because if you input -2 or 2, you get the same output, 4. It failed to one-to-one test, but it is onto because every real number has a square root.
Evaluating function. Alright, so my objective is to evaluate function and identify their domain and range. The domain of a function is all possible input values and the range is all possible output values. For instance, if we have a function f at x is equal to x squared, what the domain and range?
So, the domain would be all real numbers, and the range would be all non-negative real numbers, because squaring any real number always gives a non-negative result.
Exactly, Carlo. Now, let's try to evaluate a more complex function like f at x is equal to square root of x plus 3. What restriction do we have on a domain?
Since we can take the square root of a negative number x plus 3 must be greater than or equal to 0. So x must be greater than or equal to -3.
So, objective in proofs of functions and equivalence relations. So, alright, my objective is about giving propositions related to functions and equivalence relations. A proposition is a statement that can be true or false. For instance, if we have the proposition, if f of x equals x squared, then f of negative x equals f of x. How would we prove it?
You can prove it by substituting -x into the function and showing that it equals the original function.
Exactly. So if we substitute negative x into f of x equals x squared, we get negative x squared, which equals x squared. Therefore, if f of negative x equals f of x, and the proposition is true.
That's a clear and concise proof, babes. Proofs are essential in mathematics to establish the truth of statements and propositions. Conclusion. So we've covered each objective thoroughly by discussing modular arithmetic functions, evaluating functions, and proving propositions related to functions and equivalence relations. Understanding these concepts will surely help us solve more complex problems in the future.